So the trapezoid rule is very similar to Riemann sums, but instead of using rectangles to approximate area, it uses trapezoids. The trapezoidal rule is more accurate than the Riemann sums, any of them. And you can sort of see it pictured down here. Right? We have trapezoids. One of the reasons it's more accurate is that the trapezoid rule is going to use all of the rectangles and all of the sides of the rectangles. All right, so let's take a look at left, right, midpoint, and trapezoid rule. So in the picture on the left, right, we have the right-hand rule and the left-hand rule. So notice, let me make a little arrow here so I can point my little pointy. All right, so here on the left-hand rectangle, so the left-hand rectangle uses that value there, and then this value here, right? So that would be what that one, the left is using. So notice that we are overestimating on the left Riemann sum because this is a decreasing function. So here, as soon as the bar hits the curve, right, we use this for the rectangle. Well, look at all this stuff here. That's not under the curve, right? But that is part of the Riemann sum. Same thing over here. That part, that's not part of not under the curve, but it's part of the Riemann sum. The right-hand Riemann sum is underestimating because this is a decreasing function, right? So it's using this side, right? So it ends the bar here. But look at all it's missing all that part right there that's under the curve. Same thing here. It's using this side right here. Looks like I drew my line too far. Oh, and maybe I drew it for the left, but it stops right here. And so notice it's missing all of this under the curve, right? So both of those, the left is overestimating and the right is underestimating. Here we look at the midpoints a little bit better, right? We got some parts where the bar ends where the middle of the rectangle hits the curve, right? So if here we're going between 1 and 1.5, right? We're right in the middle here at 1.25. Where that hits the curve, that's where we end the rectangle. So it's got some parts here that go over the curve, and then it's got some parts where the curve is over the rectangle. So some things aren't included that should have been, some things should have been included that aren't, right? Or the other way around. This should have been included but isn't. This is included but shouldn't be, right? If you were just looking at underneath the curve, right? But it's more balanced, right? Between what's not under the rectangle and what is. Here's another example. So here's where the middle of the bar hits the curve, right? We have some parts where the rectangle overlaps the curve, and here we have some places where the rectangle doesn't reach the curve. Right? So here's the trapezoid rule. And so notice this is even better. Notice there's less overlap and underlap. Matter of fact, look how close that is to the curve, right? So a trapezoid, we have two parallel sides, right? And then we have two other sides that are straight lines. In this case, it's a right trapezoid. This is a straight line there. Right? So we're missing a little bit because this is a curve and this is a straight line, but we're not missing very much. All right, so here we have left, right, midpoint, and trapezoidal approximations to the integral. So here we are approximating from 1 to 2, so we're looking, our boundaries are from start at 1 and end at 2, and the equation that we're looking at is 1 over x. And the dx, right, that's that matches, right, it matches the variable for the function, right? So those two will always match, but we'll learn about that in the next series of lessons. On this one, we're just going to be mostly focusing on the trapezoid rule, and you're getting like a little glimpse of the integral. All right, so the trapezoid rule. All right, so we've seen how the midpoint rule can have an effect of balancing out the errors of the left and the right-hand rules. There's another way of balancing these errors. We average the results from the left and the right-hand rules. So the midpoint rule, let's just go back to the midpoint rule. The midpoint rule, and be good to put these in your notes, midpoint rule averages x to find f of x. Right? So it averages the left x and the right x to find the x that it's going to use to find f of x. The trapezoid rule actually averages the f of x's to the y values to find the area. Right. So the trapezoid rule averages the values of f at the left and right endpoints of each subinterval and multiplies by the change in x. This is the same as approximating the area under the graph with a trapezoid. Right? So when we find the area of a trapezoid, right, we average the two bases, and the bases are the two parallel ones. Right? So these would be the bases. We would average these, and we're going to do the same thing with the trapezoid rule. And those bases that we're averaging for the trapezoid happen to be the value for the left-hand Riemann sum and the right-hand Riemann sum. And now the page will turn for us. Right, so here, the midpoint, rectangle, and trapezoid with the same area. So midpoints can overestimate and underestimate as well. They do a better job than the right and the left-hand Riemann sums. And how you can determine on the overestimating for the midpoint, if the function is concave down, make sure this is in your notes somewhere. If the function is concave down, then the midpoint overestimates. Right? So the concavity didn't matter for the right and the left, but it matters for the midpoint. If it's concave down, the midpoint's going to overestimate. If it's concave up, the midpoint's going to underestimate. So there's the error in the midpoint rule. Right? But it is less error than in the left and right Riemann sums. So now if you're asked if it's an overestimate or an underestimate and you're doing a midpoint, right, if it's concave down, the midpoint's going to overestimate. If it's concave down, the midpoint's going to underestimate. And I might do a video where we just go through the ones we've done. We're not going to find the midpoint Riemann sums. We're just going to determine whether they were overestimates or underestimates. Right? We might do that. So stay tuned. Just to practice that. It's easier to tell if you have a graph. Sometimes unless it's a really easy function, that's not always easy to figure out whether the graph's concave up or concave down, unless of course you take the derivative, right? So you can take the second derivative and that will tell you if it's concave up or concave down. But if you have a graph, that's usually the easiest. So trapezoidal rule overview. The trapezoid rule is a little more accurate than Riemann sums because it uses trapezoids instead of rectangles. You have to know the same three things as the Riemann sum, but the equation that's used for the trapezoid rule uses the beginning and the end. We don't skip any of the terms. Right? And everything but the beginning and end is multiplied by 2. And it looks the formula looks a little complicated at first, but then once you use it, you find it's actually pretty easy. Right, so the trapezoidal rule uses the following formula. Right, so here's the formula. The asterisk is going to go next to it. We do take the change in x like before, but since we're averaging the right and left hand values, we're taking the change in x divided by 2. Or b minus a divided by 2n. Right, so when we're plugging in the values, the first value, the very first value, the starting value on the interval, right, that will be the first value you use. And then every other value you're going to use it twice for the right hand side, the left hand side, and the right hand side. And then the last value is only used once, right? Because the first value is only used for the left hand Riemann sum, and the last value is only used for the right hand Riemann sum. So here I have a little example just to kind of show you. Right? So let's just say that those the two trapezoids there, that's what we were approximating. All right. So it goes from A to C. Right, so I would have, and C is the larger one, so we would have C minus A, and there are two trapezoids, so we would have 2 times 2, and then we would have, this would be our change in x times the fact that we're averaging, so that's why there's a second 2 there in the denominator, and then we would have an A. And we would have, because A is used just for the left-hand Riemann sum. And now the b is used for the right-hand Riemann sum on the first trapezoid, and so if these were rectangles, right, instead of trapezoids, we would use b for the right-hand Riemann sum. We would also for area 1, and we would use b for area 2 with the left-hand Riemann sum. So we would use that one twice. And since there's only 2 of them, that would be the only one that would be used twice, and then we would have c, because that would only be used for a right-hand value. And that's how we would find the area using trapezoids of that particular diagram. Right? So we have 2n instead of just n for the change in x, because the area of a trapezoid is 1/2 the sum of the bases times the change in x. Right? Just a formula for the trapezoid. Times your height, times the width, which is your change in x. So here the heights are the bases and the width is the change in x. So for any method, we have to know the function of the curve, the number of partitions, and the boundaries. All right, so let's do this first one here. And it's x cubed from 0 to 4, and we're going to do this as a trapezoid rule. We've done it with everything else, so now it's going to be a trapezoid. And I will graph it as soon as the page changes, which is right now. All right, so we'll graph it. All right, so 1, 2, 3, 4. Let me just do the change in x. So the change in x tells you the width of these rectangles, and then we know that's the change in x times 1/2, right? Because it's the average. We're averaging the values. So change in x is going to be, and this was 4 minus 0, 4 rectangles, so 1, right? So each one of our trapezoids here is going to have a width of 1. So here, 0, 1, 2, 3, 4. All right, and so I'm graphing something other than blue so it doesn't blend in. So of course, 0 cubed is 0. Or maybe I should put some, it doesn't really make a difference. And then we have 1 cubed, and then we should be 1. And then we would have 2 cubed, which is 8, and 3 cubed, 27, and 4 cubed, 64. So obviously not drawing a scale, but it doesn't make any difference. Right? That gives us our curve there. Right? And so now we're going to have trapezoids. And I do kind of draw them as trapezoids just to help remind myself that these are trapezoids and that I need to make sure I use the right equation. Oop. All right, so you can see as trapezoids, I'm not going to have much overlap at all. Even though my graph's not drawn to scale, you kind of get that sense even with my makeshift graph here. All right, so the values, right? So these values are pretty easy, right? This one, the value here, 1 cubed would be 1, 2 cubed is 8, 0 cubed is 0, 3 cubed is 27, and 4 cubed is 64, right? So those are the values there. All right, so we have the sum is going to be 1 over, because it was 1, right? But we're dividing by, so instead of, let me fix that. There we go. I don't know why I had the other one in there. So the sum here is going to be 4 minus 0, but instead of being 4, right, it's going to be 2 times 4. So that's going to be 1/8. And then we take the first value, and that one's only used once, because if this were a left-hand Riemann sum, it would use the 0. Right? We're going to take the next value twice, because the right-hand Riemann sum would use it for the first partition. The left-hand Riemann sum would use it for the second partition. So we'll have 2 times 1. We're going to take the third value twice, because the left-hand Riemann sum would use it for the third partition. The right-hand Riemann sum would use it for the second partition. we're going to take the next value twice, because the left-hand sum would use it for the last partition, the right-hand Riemann sum would use it for the third partition. So we have 2 times 27. Only the right-hand Riemann sum would use the last value, so it only appears once. So notice if you've got that we have 4 partitions, n is 4, and we have 5 values. You're always going to have one more value than the number of partitions. So that's a little hint there to make sure that it's correct. And everybody but the first and last is multiplied by 2, because it would be used for the left and the right. All right, so that would be 1/8 times 0 plus 2 plus 16 plus 54 plus 64. So that's going to be 1/8 times 118, 120, 136. What are the chances 136 is evenly divisible by 8? Pretty good, because it is. So 17 is the area under the curve. Later on, once you know how to find the exact area, you can see how close we are. Right? But that one is done. Let's do another one. And that's all there is to these, by the way. All right, so here we're going to use the trapezoid rule to calculate f of x equals x squared. All right, so it's a curve, looks like that. And it's from 0 to 1 with 4 partitions. All right, so just so we know where the divisions go, 1 minus 0 divided by 4, that would be 1/4. Right? So, and that makes sense, right, because we're dividing it in fourths. We have 4 partitions, and the width is only 1 for the whole thing. So this will be 1/4 and 1/2 and 3/4 and 1. Right? And so here's our first trapezoid, our second trapezoid, our third trapezoid, and the fourth trapezoid. Okay. And then I'm going to write the values underneath. Right? So we're just squaring. So 1/4 squared, that's 1/16. 1/2 squared is 1/4. 3/4 squared is 9/16, and 1 squared is 1. All right, so now we're going to sum up those areas of those trapezoids. So we have, so it's still going to be the 1 minus 0 divided by 4, right? But now instead of that, it's going to be, we're going to take that and divide that in half. So it's going to be 1 minus 0 divided by 2 times 4. And then we have, so the first value, the f of x naught, that's only going to be in there one time, right? And oh, we didn't write that down. The very first value is right here at 0. So the very first value is 0. Right? So I'm going to actually write it in without plugging in first, just to make sure we're very clear. And it's not a bad idea if this were an AP test to show them you know what you're plugging in. Right? So we would have f of 0, and then we would have 2 of the f of, that's supposed to be an f. That's a horrible looking f. 2 of the f of 1/4, and 2 of the, just make it an f. I keep wanting to make parentheses instead of my f's. 2 times f of 1/2, and 2 times f of 3/4, and then just 1 f of 1. All right, so this is 1/8, and then f of 0 is 0. This would be 2 times 1/16 plus 2 times 1/4 plus 2 times 9/16 plus 1. All right? So 1/8 times 0 plus, definitely going to cancel out that 16, so that would be 1/8, plus, this would be 2/8. No point in me reducing because I need to add it to the 1/8. So this would be 2/8, would be 2/4, and 2/4 is the same as 4/8. So if you're okay, I'm just going to make that 4/8. And then we'll cancel out the 16, so that will be 9/8, and then 1. And 1, of course, is the same as 8/8. We may as well make that 8/8 so we can add it. All right, so this is going to be 1/8 times, so we've got 17, 18, 22 eighths. All right, and we could reduce some. Because while it's okay to have unsimplified answers on the AP test, when we're actually solving, when you want to present something, you'd want this simplified, right? So this would be 11/32. And there we go. This one is done. Okay. So once you get the hang of the right and the left, the midpoint's not too difficult. Right? And notice the trapezoid is not too difficult. The midpoint's not too difficult either, but this is the trapezoid. Trapezoid is not too difficult. Just notice it's using every value, right? And it's using all the values but the endpoints twice. All right, so let's, same equation, different interval. So use the trapezoid rule to estimate the area under the curve. X squared, 4 intervals from 1 to 2. All right, so 1, and then, of course, if we take 2 minus 1 and divide it by 4, again, that's going to be 1/4. So if we're starting at 1, the next value is going to be 5/4, and then 6/4, which is 3/2, and then 7/4, and then 8/4, which is 2. And here is our function. So let's draw in our rectangles. Trapezoids. There we go. All right. So we're going to have the change in x will be 2 minus 1, and it's going to be 2 times 4, right, because we're averaging the two values, the right-hand value and the left-hand value. And so then we would take that and we would multiply that by f of 1, and 2 times f of 5/4. I don't think I'm going to have enough space. I'm going to have to move this down a little bit. Plus 2 times 3/2 f of 3/2 plus 2 times f of 7/4, and then plus f of 2. Right, and then we'll plug in the values, and we'll get our answer. Sorry for the 5-second break. Allergies, desperate need for tissue. So this is going to be 1/8 again. So f of 1, that would just be 1 squared. That's going to be 1. And then 5/4, that would be 5/4 squared. That's 25/16. 3/2 squared is 9/4. 7/4 squared is 49/16. And then we just use the 2 squared, or 4, one time. And yep, got all the parentheses I needed. Okay. So 1/8 times, so 1 plus, this will cancel, right? So that's going to be an 8 now. So we have 25/8 plus There's really no point in me reducing that because I needed to have a denominator of 8 to add it to the 25/8. Oh, and I guess I really should make this 8/8. There we go. So that would be 18/4, but we want 8ths, so that would be 36/8 plus, and we can reduce the 2 and the 16. That's going to be 49/8. And then 4 would be 32/8. All right, so now we will add those together. And this time I think I'm going to use a calculator because that's a lot to keep keeping in my head. And 32 is 158. Well, that'll reduce nicely. So that's going to, well, we'll reduce a little bit anyway. So that's going to be 75. So then 75 30-seconds, because this would be 150 and 8 are both divisible by 2. All right, and that's the area under this curve. We did another one. Let's see if I'm going to do another problem or if I'm going to take a break. It all depends what the next problem is. If it's one just like this, I'll do it. If it is, nope, this one I want to do on a separate video. So I'm going to end this one here. The next video, I've done just, I've done enough, I think, trapezoid rules, you get the idea. The next one is we're going to look at a table, and we're going to do a left-hand Riemann sum, a right-hand Riemann sum, a midpoint, and a trapezoid, and how many subintervals if they don't tell you. All right, that's the next video. Bye for now.